name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunications Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing them. Welcome to talk number 10 in the ITS RF Measurement Seminar Series. The topic of today's talk is noise diode calibration of RF measurement systems. At ITS, we've used noise diodes for over 30 years to calibrate the gain and the noise figure of our measurement systems. Noise diodes can be used to calibrate the gain and noise figure of any RF system, whether it's a measurement system or a receiver, and we have used diodes for such purposes over the years with systems other than measurement systems. With that said, what I'm going to do today is give a derivation of the equations that we use for gain and noise figure when we're calibrating with the noise diode. I'll also introduce it with a brief description of what a noise diode is, why we use them, and then the majority of today's talk will be a lab session where we'll actually show the use of a noise diode as an adjunct, as a bonus. We'll also describe the use of a couple of different low noise amplifiers and show why sometimes a low noise amplifier can be put into a measurement system and not do any good for the measurement system, could even degrade the measurement system. Other times why we need to put in a low noise amplifier, but we also need to add some attenuation between the output of the LNA and the rest of the measurement system to actually optimize noise figure and dynamic range, which maybe seems or could seem a little bit counterintuitive. So with that said, when I'm doing the derivations, linear quantities are going to be written in lowercase, so linear gain is a lowercase g. Decibel quantities will be written in uppercase, so 10 log of any linear quantity will be the decibel quantity, which will be written as a capital letter. It's just a convention. We've used it before in this series. Now, noise diodes. First of all, noise diodes are broadband noise power sources. They are normally, and in fact to be useful they need to be, calibrated for a particular power output. We'll talk more about that. In order to be useful, if you're not going to use a noise diode to calibrate a system for gain and for noise figure, a typical alternative choice would be a signal generator. In which you would have a carrier wave that would be generated, and the carrier wave would probably be swept across some frequency range of interest of some sort. Now, the trade-off between using some sort of carrier wave swept source, which is a signal generator, as opposed to using a noise diode is that, relatively speaking, noise diodes are relatively small. I'll hold one up here momentarily. Here's a noise diode that's been packaged for a person to use right out of the box. So relatively small. They're relatively lightweight. They are relatively rugged. Now, I'll emphasize the word relatively rugged, because if you hit it or drop it, you could still break it, of course. And they have a relatively low power requirement. Typically, the power requirement is 28 volts DC at a current draw of about 50 milliamps. So if you compare this as a calibration source, which you might need to use at the top of a tower, you might need to use it in a mobile application in terms of its size, its weight, its relative ruggedness, and its low power requirement, as compared to a signal generator, which is something that would be typically a 19-inch size rack mount box like this. You can see the advantages of the noise diode if you can use it. One application that I would like to mention, in fact, for noise diodes that was of some particular interest back in the early 1990s, specifically from 1989 to about 1993, was noise diode calibration of a spacecraft called the COBE, the Cosmic Background Explorer. And this was the spacecraft that was put into Earth orbit and was used to calibrate, to actually observe the anisotropy, that is the lack of uniformity in the cosmic microwave background radiation that's left over from the Big Bang of about 12.5 billion years ago. So in this particular spacecraft, they use noise diodes pretty much the same way that ITS uses them, and I'll diagram it in a moment. Basically, the noise diode is inserted into the measurement system at a point that is just after the point in the system where the antenna would be connected. So you switch between the antenna and the noise diode and thereby calibrate everything in the RF path in the measurement system except for the antenna itself. So the COBE spacecraft carried at least one noise diode. I'm guessing it might have carried more than one. They typically put backups in. And they used noise diodes to calibrate the COBE spacecraft, which in turn had some sensitive microwave radiometers on board that were used to measure the anisotropy and the microwave background radiation from the Big Bang. They also, by the way, used an alternative noise source, which was the sun. And in order to use that, they couldn't point directly at the sun. It was too strong a source, so instead they pointed at an attenuated solar source, which is the moon. And in effect, they were using that as a sort of natural noise diode, a broadband noise source with known noise characteristics. So, with that said, I'll describe how we typically use noise diodes in the measurement system. As I just said, the key in using a noise diode in this kind of application is to be able to put the noise diode into, if this is the measurement system that we're using, which in ITS applications typically has an antenna attached. What we want to do, what we need to do, is be able to break this line right here and attach a noise diode into the line right at that point so that we're calibrating everything in the measurement system, including whatever we have here in terms of an RF line going into the system and anything that might be in the RF line. Calibrate all that with a noise diode, and the only thing that is left as an unknown is the actual antenna calibration factor itself, and we can, and we have to, in fact, handle that separately. So, in today's lab, which is going to occupy or constitute the majority of this talk, what we're going to do is use the ITS RF front-end source for the radio spectrum measurement system. And in this system, here's the way that we've got it built. We actually have a front-end box that can be switched between any one of a number of antennas. These antennas go into the box like this through selectable antenna input ports, and then inside the box, I'll give myself some space here, inside the box what we have is a noise diode source down here with a power supply right here, which can be turned on and off via remote control, and this injects in just like this. So we have a set of antennas noise diode coming in like this. We have a rotary switch, and the rest of this we've drawn in previous talks. This then goes through a 0 to 70 dB RF attenuator. We then switch into a bank of any one of a set of bandpass filters, some of which are fixed, some of which are tunable. I won't belabor it by drawing all the actual rotary switches. Just draw it this way. We go into a bank of bandpass filters. We then go into any one of a group of low noise amplifiers in the box, and then coming out of the low noise amplifiers, we then pass down through some kind of RF measurement line. Hopefully a little straighter run than I just drew, and then possibly into an auxiliary low noise amplifier and any other components that we might need. And then typically at this point we'll run into a spectrum analyzer, or any one of a set of ancillary measurement boxes. For example, oscilloscopes, etc. And then finally we wind up with our final data output at the end of the system. So again, the key here is that the noise diode, when we switch it in and when we use it in the lab today, is in fact going to be taking all of the gain and noise figure of this system into account when it's turned on and when we calibrate with it, except for whatever line we have attaching any one of our antennas into the front end box. So we try to keep those lines short, and we try to know whatever their loss factors might be if we're trying to get a calibrated measurement at the antenna itself. Any problems with that? Okay. Now, having drawn it that way, remember that you can calibrate any receiver, you can calibrate any black box system for gain and for noise figure with a noise diode, of course. Now, let's go into the theory. What I'm going to do is derive the equations for gain and noise figure using a noise diode. And I'm going to forward board, because I want to draw a picture of the system up here and then draw the equations underneath it. In terms of the derivation of the equations, here's what we're assuming we have. We have some kind of a box. It could be a measurement system. It could be something other than a measurement system, like a radio receiver. And in this box, in principle or in theory, what we have is a source of noise which represents the inherent internal noise generated by the measurement system. We've talked about this in past talks, of course, at length. And the inherent noise generated by the measurement system is assumed to be added to whatever the input power is that's coming from the outside world. It could be coming from an antenna, it could be coming from whatever source we have, and what we want to do is calibrate this system, and then having summed whatever the input is with the inherent noise that's generated inside the measurement system, we have an ideal noiseless gain stage that has a linear gain, G, and then we have the system output here. And where the noise diode comes into the picture is, we're going to use it as a source of external noise power called an external noise ratio. Excess noise ratio, sorry, I misspoke. Excess noise ratio. So here's our noise diode. We're going to hook up at this point, and we'll connect it in turn to a 28 or so, it varies depending upon which diode you're using, 28 volt power supply, which can be turned on and turned off at will. We'll demonstrate this in the lab section. So what we'll do is look at the power coming out of the system when the noise diode is turned on, and then we'll look at the power coming through the system when the noise diode is turned off. And everything else will come out of that. Now, definitions. Okay, first of all, first item to define is noise factor. Noise factor is the ratio of noise power in the device, or the system, whatever you want to call it. Device/system, whatever it is. That's not a ratio, so in fact I'll clarify by not writing it with a slash. But the noise power in the device divided by the thermal noise, KTB. And you remember, of course, that K is Boltzmann's constant, which is approximately 1.38 times 10 to the minus 23 joules per degree Kelvin. Okay, B is the bandwidth of the system, T is the system temperature in degrees Kelvin. That's the noise factor. The excess noise ratio, ENR, is equal to the noise generated in the device minus the inherent KTB that we can't get away from, divided by KTB. So that is, in other words, noise factor minus 1. I'm writing these lowercase, so again, these are all linear equations. These are all linear quantities. And so ENR is the fraction, in effect, the fraction of the power that's available in excess of KTB, like so. Okay, that's straightforward enough. Now, in decibels, we have a quantity noise figure, which is predictably 10 log of noise factor. And we have excess noise ratio written in decibels, so capital letters, which is equal to 10 log of the linear quantity excess noise ratio. Probably clear enough. One thing that I wanted to mention. So excess noise ratio is often the specification that you'll see for a noise diode. For example, you might see a noise diode specified as a 20 dB ENR noise diode. That can also be written in terms of noise temperature, neglecting the factor of 1 there for large T's. Just for example, suppose that we had a 20 dB ENR for a noise diode. That could be written as the temperature of the noise diode divided by room temperature, 290 Kelvin, and that would be equal to 10 to the power of then 20 here, divided by 10. Times 290, so that is going to be 100 times basically 290. That's basically going to be, and I did, yeah, 29,000 Kelvin. Yeah, I just want to make sure I was doing that right. Actually, this isn't equal to, but what you do here is take this ratio. Temperature noise diode divided by room temperature is going to be equal to 10 to the 20 over 10. That implies, let me write it this way. That implies that the temperature of the noise diode is equal to 100 times room temperature, 290 Kelvin, which which gets us the 29,000. So you could also see, my point being that you could also see a noise diode specified as a 29,000 degree noise diode. And if you do, you can basically take that quantity divided by room temperature, take 10 log of that, and you'll get the 20 dB ENR or whatever it might be for any given noise diode. So now, forward board. Okay. All right. So as I said, the basic approach is we turn the noise diode on, we get a power level reading. Turn the noise diode off, get a power level reading. We use the difference between the two to get the gain and the noise figure of the system. One thing to keep in mind as a practical matter, just a practical issue to be aware of, is that it's important to be able to, or it's important to be sure that the noise diode is matched in terms of impedance to whatever the measurement system is, or the radio system is that you're going to be measuring. Sometimes, depending upon how the noise diode has been manufactured and packaged, sometimes it's necessary to put some RF attenuation. Typically, we found a 3 dB attenuator between the output of the noise diode and the measurement system. It's not always necessary, but it's something that's important to check just as a practical matter if you're using this. We'll assume here that everything is functioning properly in terms of impedance matching, in terms of the equations that we're doing. Okay, so let's walk through this fairly expeditiously. So, I'll number the equations as we go through here. These are linear quantities. The power on that we measure when we turn on the noise diode is going to be equal to the noise factor times the gain of the system times KTB, plus whatever the excess noise ratio is, also times G KTB, and that, of course, is then noise figure plus ENR, quantity times G KTB, like so. Now, when we turn off the noise diode, the power that we measure when the diode is off is just going to be the noise factor of the system times G KTB, and this is just a bit of terminology. The Y factor is equal to linear quantity, lowercase y, is equal to the ratio of P on divided by P off, which is noise factor plus ENR divided by noise factor. Okay? And if we want to write this in terms of decibels, then we write capital letter Y is equal to 10 log script Y, which is going to be equal to 10 log of P on divided by P off, which is of course equal to 10 log P on minus 10 log P off, which is equal to capital letter, decibel quantity, power when it was turned on in decibels minus power when it was turned off in decibels. So these are capital letter P's here. Okay, so there's your decibel Y is just the power on minus the power off in decibels. Now, next little equation. The noise factor then is equal to the ENR divided by Y minus 1, and so that implies that the noise figure, capital NF, which is equal to 10 log of this quantity, ENR, over y minus 1 is therefore equal to the decibel quantity, excess noise ratio of the noise diode, which is supposed to be a calibrated. It's supposed to be a calibrated quantity, minus 10 log of y minus 1, which is ENR minus 10 log of 10 to the power of capital Y, the Y factor capital Y, divided by 10, minus 1. I'm going to circle that. Okay, so if we want to know the noise figure of the system, we turn the thing on, turn it off. We look at the power on versus off in decibels. That's this capital letter Y. We divide that quantity by 10. Take 10 to that power, subtract 1, take 10 log of that, subtract that from the ENR of the diode, which is calibrated. And now we have the noise figure of the system. One thing to note here is that as Y gets to be about 10 dB or more, this quantity approaches just 10 to the Y over 10. And so what you can do as Y gets to be about 10 dB or more is just approximate this as ENR minus Y if Y is greater than about 10 dB, greater than or equal to 10 dB as it gets up there. So if you're doing something, if you're just eyeballing it and you don't have a pocket calculator, if you turn the diode on and off and you see more than a 10 dB difference, you can pretty much take whatever that difference is subtracted from the ENR and you'll get that. And that really does work. So now, lastly, we'll look at the gain. 6. We want to get the gain through the system. So the linear quantity G is equal to the linear power on minus power off divided by the ENR times KTB. And that implies that the decibel gain, which is 10 log of the linear gain G, is just 10 log of P on minus P off divided by ENR times KTB, and that's going to be, I was just debating how much I want to write this. I'll go ahead and write it out. 10 log of P on minus P off minus, down here, 10 log of ENR minus 10 log KTB. So just break those out. And so that's equal to 10 log of the decimal 10 to the power of the power on in decibels over 10 minus 10 to the power off in decibels divided by 10 minus, this is just the excess noise ratio in decibels. Again, that's the calibrated quantity, so we know that. Minus 10 log of KTB. So circle that in green. Okay, so now we have gain given by this equation, and we have noise figure given by this equation, and in both cases all we have to do is measure power on in decibels, power off in decibels, and be aware of the excess noise ratio that we've calibrated for the noise diode. We also need to know KTB for whatever we're doing, and of course presumably we know that when we're measuring through the system. So what we do operationally, of course, is not just do this at one frequency for a measurement system, but do it for a whole set of frequencies in a measurement system across some range that we're going to perform a measurement in. And we then let a computer calculate these quantities for every single frequency at which we made the measurement. And what we finally obtain, and I'll draw it here, and we'll see this in a moment, what we obtain are a pair of curves. One curve that we could graph, and I'll draw this just a little bit better. One curve we can graph, we'll graph off the left, will be the noise figure, and the noise figure might look, actually I'm going to draw this the way the software does it that we're going to see in a second. So actually this axis will be gain, and this will be say 40, 30, 20, 10, and 0 dB gain, like so. So we might measure and calculate gain across some frequency range like this, like so. And again, oh, and I should note that this is a frequency range. I'm not going to write it in here. This is frequency range across here. Get gain as a function of frequency because we do this calculation for gain at a set of frequencies across the range, graph it like that. And then we can graph noise figure in a different color. We'll assume that we have a noise figure of a few dB floating along something like this down here. And we'll graph that over on this axis, and now this might be something like, again, 10, 20, 30 dB and so forth of noise figure on this axis. So it's easy to produce a graph that shows both the gain and the noise figure as a function of frequency across the measurement range, where what we've actually done, of course, is do this computation for a lot of individual points running across. Now again, as I said, if y gets to be greater than 10, well, 10 or greater, then you can even just eyeball it. And if you can't get that much of a difference and you don't have a computer, you can, of course, use a pocket calculator and do these calculations with a pocket calculator. And I'll demonstrate that in a second with a manual noise diode. So, with that said, any questions before going to the lab session? Yeah, Paul.
Frank, typically what are the uncertainties on the excess noise ratio for one of these noise diodes?
That's a good question. The question, in case the people in front didn't get it, is what's the uncertainty in noise diode excess noise ratio? It can be calibrated to within a fraction of a dB. You can get calibrated noise diodes that are calculated to within a fraction of a dB. Here at ITS, we've actually had I was going to say a program, or a process running recently anyway, where we've actually gone to a lot of trouble to calibrate all of our noise diodes that are in our inventory right now against, and correct me if I'm wrong about this, Randy, against a noise diode which has itself gone through a rather precise calibration independently. Is that true?
Yeah, we're still working on it.
And you're still working on it. What would you say the uncertainties are in those noise diodes calibrations?
I don't know, because we haven't fully developed the system.
I can tell you that repeatability is typically within a fraction of a dB, Paul, and I believe, based upon talking with people in NIST, that the uncertainty can be a fraction of a dB in it, in the noise diode calibration. It is possible that noise diodes could vary in their behavior as a function of temperature. It could even vary as a function of time, so it's probably not a bad idea to have noise diodes recalibrated every so often. Any other questions right now? What we're going to do next is go ahead and go into the lab section. Okay, this begins the lab section of talk number 10 on noise diode calibrations. What we have here is a display coming out of a spectrum analyzer, and this spectrum analyzer has been put into a detection mode, which is RMS average. All of the calibration that I'm going to show here can be done with a spectrum analyzer that lacks an RMS detection mode if you in fact use a sample detection mode with a video bandwidth that is at least a factor of 10 narrower than the resolution bandwidth. For example, you could do this with a conventional spectrum, I say conventional, with an analog spectrum analyzer, which is running in a 1 megahertz bandwidth with the video bandwidth set to, actually I'd even go narrower than 10, set to about 1 kilohertz, a factor of 100, so, or a factor of 1,000 even. a factor of 1,000 narrower with the video bandwidth, 1 kHz video bandwidth, 1 megahertz resolution bandwidth with sample detection will get you the same results in terms of the noise diode calibration. But here I'm going to go ahead and use root mean square. What we're doing is looking at a span of 500 megahertz from a beginning frequency of 1 gigahertz to a stop frequency of 1.5 gigahertz. This is just a convenient frequency range for us to perform the calibration over. And because I right now do not have any amplification turned on inside the spectrum analyzer, nor do I have any external amplification, I can use the trick that we've looked at before to estimate with my eyeball exactly what the noise figure of this ought to be, but we'll do this with a noise diode manually and just verify that my trick works. We're going to get the noise figure of this thing. We know that we're reading a power level of minus 104 dBm, and we're working in a 100 kilohertz bandwidth, so do the math. We know that in a 1 hertz bandwidth, KTB is minus 174 dBm. We know, therefore, that in a 100 kilohertz bandwidth, which we're running here, would be 50 dB higher than that. That would be minus 124 dBm. But we're running at minus 104, so we seem to have a 20 dB noise figure. Well, and by the way, the reason that I can do this is because I know that I think I know that the gain factor between the displayed power values of these points and their actual power values is in fact a linear gain factor of 1, a decibel gain factor of 0. In other words, that these points are accurately known in terms of power already. So the next thing I do is, having screwed that manual handheld noise diode onto the front panel that you saw in the whiteboard section of the talk, I turn on the, I actually have to connect the noise diode to a 28 volt source, check it, make sure it really is 28 volts before I put it onto the noise diode. Okay, we turn on the noise diode. So here we see diode with power on, and here we see diode with power off. We know that the power off is minus 104. Power on is, minus 98. It rounded to the nearest dB. So that's a 6 dB change, power on versus power off. So if we use the equation that we derived on the whiteboard, we'll actually go ahead and do this real quick. We'll take capital Y is 6 dB. We'll divide that by 10. That's 0.6. We take 10 to that power. That's 3.98. We subtract 1. That's 2.98. We take log of that number. That comes out to be 0.4744. 10 times is 4.7, and here's the key part, this noise diode has calibration factors stamped on the side. It's supposed to be a 25 dB excess noise ratio diode, so we subtract 4.7 from 25, and we get 20, I did that wrong, we subtract, 25 minus 4.7 gets us 20.3. So I eyeballed it at a 20 dB noise figure. We use the noise diode, we get 20.3 for the noise figure of the system. It's not a surprise, but it's kind of a verification that this can be done. You can do it with a pocket calculator, and if this on versus off ratio that we see here, in fact, were to get to be 10 dB or larger, remember that you could just take that difference and subtract it from the ENR of the noise diode, in this case 25, and you'd have the noise figure directly. For example, if you turn this on and off and you saw a 20 dB difference between on and off, and you subtracted that from the 25 dB ENR of the noise diode, you could say, okay, this thing has a this thing has a 5 dB noise figure, and if you actually do the math, you'll find that it's within a fraction of a dB of 5 dB. Okay, now, having done that manually, any questions about that part of it? Pretty straightforward, I think.
Frank, are these diodes biased in the knee region to generate the noise?
I believe they are. I believe they are, Bob. The question was, are these diodes biased in the knee region to generate the noise? I believe they are. I'd have to actually check to make absolutely certain of that.
Well, I know the diodes, for instance, they use noise bridges for antenna measurements or that way, but I wasn't sure in this case similar.
Ah, okay. Yeah, I believe it is. Now, having done that, the next thing that I'm going to do is to calibrate this spectrum analyzer's noise figure, but not just the spectrum analyzer's noise figure. I'm going to calibrate the spectrum analyzer with the ITS RF front end box attached to it, which you'll recall has a low noise amplifier, has a lot of low noise amplifiers inside it. And we have one of these low noise amplifiers, the one that works from 1 to 2 gigahertz, turned on. And what we're going to do is demonstrate a computer-controlled noise diode calibration with noise diode in the front of that RF box, just the way I drew it on the whiteboard a short while ago. And we'll see what we get for noise figure when we're going through that first low noise amplifier and then going out of it, out of the front end box into the spectrum analyzer. With that said, if this is a good time, Randy Hoffman, who was the person who led the software development, will walk us through a computer-controlled noise diode calibration.
Okay. So this has two devices that we connected to. One is the pre-selector, and the other is a spectrum analyzer. And we then have a program that is the swept calibration procedure.
And Randy, by swept calibration, I think you mean that what you're going to do is take 601 data points across this frequency range of interest from 1 gigahertz to 1.5 gigahertz,
Yeah.
and perform this Y-factor calibration at every one of those 601 points to generate a graph similar to what I drew on the board a little while ago that'll show us the gain and noise figure across that range, right? Yeah.
We normally set up all the settings in a table that then designate how we're to sweep, what kind of bandwidth, the number of points, those kind of things, and it has our ENR in there. We have a choice of either using an external noise diode or internal. This is not the ENR that's associated with this spectrum, this pre-selector. It's that we're actually using the value that's in the table. So all we have to do is then run it, and it'll first acquire. You can see the noise diode turned on there on the pre-selector. Let's take a trace. It's a 5-second trace. It should plot that. So that's with the noise diode on. And we use average detection, and that's with the noise diode off. And then it computes the gain noise figure. Now you see a few little spikes in there, and those are due to some signals actually coupling in the system.
Some ambient signals are coupling into the system. These spikes right here. And so what we're seeing here is a graph, again, very similar to what we saw on the whiteboard earlier. We have two curves drawn. On the left vertical axis, we have the gain drawn as a green curve, and our gain here is running about 12 dB. And the noise figure here is running anywhere from almost 0 to as much as about 3, so maybe about 2, typically 2 dB of noise figure on the blue curve, which is plotted on this axis over here. One thing that I should point out is that when we ran this particular calibration just now, we did turn on an internal preamplifier inside the spectrum analyzer, which has probably about a 7 dB noise figure, and this ripple that we see in the noise figure is actually a real characteristic of that amplifier. It's actually not behaving at all well, and we knew that before we did the talk. We intentionally went ahead with it to show that even if you have a component that isn't behaving just the way you'd want it to, that's okay in the sense that you can calibrate its behavior, and if you're making measurements, you still know what your system's actual noise figure really was, and you know what your system's actual gain is. And this gain is a function of the gain in the low noise amplifier in the RF front end box the losses between the front end box and the spectrum analyzer and the noise figure of the spectrum analyzer itself with its own low noise amplifier turned on. Yeah, these spikes, as you said, Randy, these are basically not good data points, but if we're taking a measurement, we can be aware of that, we can note these, and there are a variety of ways of working around that. These are due to some strong ambient signals that are coupling into the measurement system. But that's the basic approach if you're doing it with a computer-controlled system. Obviously, it's very convenient. Now, what we're going to try, well, first, any questions on that up to this point? Okay. Now, what we're going to try is, using a step attenuator, we're going to listen for it, hear that click. We just clicked in 10 dB of RF attenuation between the front end box and the spectrum analyzer. This can represent 10 dB of line loss between the front end box at the top of a mast, where an antenna might be located, and the rest of the measurement system. Now, if you would, Randy, run the calibration again, remembering that we had 12 dB gain and about a 2 dB noise figure. Here we're running cal again, diode power on, then diode power off. There's the diode power on curve, 601 points from 1,000 to 1,500 megahertz. We get the power off from 1,000 to 1,500 megahertz, same 601 points. Now look what happened. The noise figure of the system has gone up to more like about 5 to 6 dB because of that, we'll call it line loss that we injected, that extra 10 dB. And the gain correction has gone down to something like about 3 to 4 dB across here. By the way, I should point out that this gain curve is important when we're making a measurement, because any data point that we would collect at any given point, at any given frequency, let's say, for example, at 1,300 megahertz, any data point that we read off the spectrum analyzer at 1,300 megahertz would have to be corrected for the system gain, which at this point is about, say, 3 dB. So if we read a power value off the spectrum analyzer of, say, minus 100 dBm at 1,300 megahertz, we would actually have to subtract 3 from that and then store that as a calibrated power level of minus 103 dBm. That's the point of getting the gain, of course. Noise figure, on the other hand, is important to know because this tells us how sensitive we are. Now we say, gosh darn it, we put that long line in there, our noise figure went up, this has degraded our ability to see weak signals. So, what are we going to do about that? Well, we'll get an auxiliary preamplifier hooked up, and we'll put the auxiliary preamplifier at the bottom end of the RF line, right at the input to the spectrum analyzer. And I'm going to do that by wiring it in here momentarily. All right, so we'll bring the RF line in. Bear with me for a moment while we do this. You can't see this on camera, but we have the RF attenuator feeding into a little auxiliary preamplifier. Let me make sure I get the right end here.
Frank, what are those controls on the top of the unit there?
The controls on top of the attenuator are the attenuator settings.
I see.
I can step it in 10 dB steps and 1 dB steps, and we'll see the use of that. Okay. And then we have a okay, turn on the preamplifier, 15 volts, like so. Okay, now, sorry for the delay there momentarily, but we've now put in an auxiliary preamp, electrically speaking, at the bottom of that long RF line at the input of the spectrum analyzer, remembering that our noise figure here was running about 5 or 6 dB, and gain was about a 3 or 4 dB. Let's go ahead and rerun the calibration, please, Randy. Diode on. Collect the data points. Diode off. collect the data points. Now let's see what happened. Huh, isn't that interesting? Our gain values are a little higher. They're about 5 dB now, so that's about 1 to 2 dB higher than they were. But not only did our noise figure not improve, our noise figure has actually degraded by about a dB or 2. So, just sticking an amplifier into a system doesn't always solve all your problems. This amplifier doesn't have a particularly low noise figure, nor does it have a particularly high gain value, and putting this particular low noise amplifier into the system has actually degraded our performance in terms of sensitivity.
So in placing the amplifier where you did, you brought up the signal and the noise together.
Yeah, the statement is putting the amplifier where I did brought up the signal and noise together. So we can't see any weaker signal than we could before. We haven't benefited ourselves in any way. In other words, this amplifier isn't a very good choice for this particular application at this particular point in this particular measurement system. But we have another amplifier available that has significantly higher performance. This amplifier has a much lower noise figure. It's got much more gain. And of course, these are the problems that we go through when we're setting up measurement systems. These are also the problems that radio system designers have to face when they're designing receivers. Now, we'll go ahead and plug this in. The second amplifier, higher performance amplifier, which means lower noise figure and higher available gain. And I'm just looking here to make sure I've got everything hooked up right. Yep. Again, it's in the same places as the first amplifier. It's at the bottom, as it were, of our RF line, just at the input of the spectrum analyzer. Randy, if you'd do the honors, please. Diode on. Gather the data points. Diode off. Gather the data points. Much better. We've got our noise figure almost down to where we started. Noise figure is running about 4 to maybe 5 dB across here. So in terms of sensitivity, we've done ourselves a lot of good by using a low noise amplifier at this point in the system that has a lower noise figure. Now, let's take a look at the gain. The gain is running anywhere from 28 to as much as 30 dB. This is the correction factor that we have to add to our data points as we collect them off the spectrum analyzer. We have to actually, for example, take a point at 1,450 megahertz, and basically whatever power level we read off the spectrum analyzer, we subtract 30 dB off of that to get the power level that was coming in at the input of the measurement system. But this gain is going to cost us dearly when we're doing measurements, because it's eating up, and we've talked about this in some earlier talks, but I want to bring this home today, it's eating up the dynamic range in our measurement system. In other words, a fairly weak signal is actually going to overload our measurement system. That's a problem. Now, do we need all that gain? No, we don't. The only place where gain will do a person good in a measurement system is if they are trying to get higher gain with a directional antenna on a point source in space. If you're trying to look at a distributed source in space, like the cosmic microwave background radiation, a directive antenna does you absolutely no good whatsoever. And even if you're looking at a point source, other than the gain in the antenna, more and more gain in the measurement system is not only not a benefit, it is actually a detriment, because I say it eats up the dynamic range. And in fact, I'd like to demonstrate that here momentarily. We'll switch back to the spectrum analyzer display and I'll show you something. And before I do, Randy, if you would go to manual mode on the spectrum analyzer. The software locks out operator control when it's running. And now that we're in manual mode, I'm going to switch the projector back, excuse me a moment, to the spectrum analyzer, show you what's going on here with this amplifier turned on versus turned off. Get this thing sweeping. Right now we're looking at the spectrum analyzer display with the amplifier turned on. We have these ambient signals that are actually leaking into the measurement system. Now I'm going to turn off the I'll do this. Trace one view. Now, trace two, clear right. Now we're going to turn off the amplifier. Whoa! There's the measurement system noise floor. There's the effect of the amplifier. Now, this amplifier is eating up about 10, 20, about 25 dB of dynamic range in the system. We're losing about 25 dB of power range that we could otherwise be making a measurement with for basically no good purpose, no good reason whatsoever. Now, I'm going to demonstrate how if we insert attenuation after the output of the amplifier. I have to do a very quick rewire here. Actually, see, we'll bring this in here. No, sorry, bring this in here. There we go. What I'm going to do is put the step attenuator between the amplifier and the spectrum analyzer so that we can actually demonstrate how we can reduce the gain and have a negligible impact on noise figure to a point and optimize now the overall behavior, the overall performance of our measurement system. Wire in the amplifier, amplifier into step attenuator, step attenuator wired into spectrum analyzer, like so. Okay. Having done a quick insertion of the step attenuator in here, now I'm going to attenuate the output of the low noise amplifier going into the spectrum analyzer by 10 dB. Watch what happened. Oh, excuse me. I've actually got to freeze trace 2, go back to trace 1, get it running, and let's see. Is on. Oh, amplifier is not on. That would explain it. There we go. Okay, amplifier on. Now, remember, this is the noise floor of our measurement system. I actually had 10 dB of attenuation in before that I've actually removed, so we're actually eating up 10, 20, 30 dB of dynamic range needlessly. So let's go ahead and put in 10 dB, and in fact I will demonstrate it like this. We'll view, and then clear right. 10 dB down, like so. 20 dB, like so. 30 dB. Let's start there. We're going to calibrate the measurement system with 30 dB of attenuation inserted between the output of the low noise amplifier and the input of the spectrum analyzer, and let's see how much impact that actually has on the gain and noise figure of our measurement system. Okay, we're now going to run the noise diode calibration. So we have points taken with diode turned on. Points taken with diode turned off. Now look what's happened. We inserted 30 dB of attenuation after the output of the low noise amplifier and before the input of the spectrum analyzer, so between the amplifier and the spectrum analyzer. Having done that, our noise figure has barely changed at all, but our gain factor has dropped down to a gain correction of about 8 to 9 to 10 dB, and as we saw when we were watching the spectrum analyzer screen a moment ago, we got 30 dB of dynamic range back available again to make measurements with. So now we can see signals that are 30 dB stronger than we otherwise could have. we can see weak signals that are virtually as weak as we could see before we put into 30 dB of attenuation. And we made this improvement not by getting attenuation out of the measurement system, but by putting 30 dB of attenuation into the measurement system. And we wanted to show you this today to help bring home this lesson that the important thing to keep in mind when designing any kind of measurement system or looking at the performance of any kind of a receiver is that it's important to use the Reese equation that we talked about a few seminars back to actually optimize the noise figure and the dynamic range of the measurement system both, and that more gain in an amplifier is not necessarily a desirable quantity or desirable factor to have when you're making a measurement. It's not having more gain, it's having the right amount of gain, typically optimizing the gain factor against the noise figure. One final one, just to demonstrate that we do have to strike a balance here, I'm going to add another 6 dB, 1, 2, 3, 4, 5, 6 dB of attenuation in. Now this should begin to degrade the noise. This should begin to degrade the noise figure of our system somewhat. Go ahead, if you would, Randy, and run the calibration again. The reason I know that is on a spectrum analyzer, when we put into 30 dB of attenuation, I watched to make sure that I stopped when the output of the amplifier coming through the attenuator was about 3 dB above the noise floor of the spectrum analyzer. Meaning that when we turned on the amplifier and turned off the amplifier, the power coming out of the amplifier was about equal to the spectrum analyzer's noise floor. Here we've now gone 6 dB beyond that. Now what's happened is we have in fact seen our noise figure degrade substantially. The noise figure's gone up to about 8 to 9 dB. So we were dead on, probably where we wanted to be, when we had just 30 dB of RF attenuation in. So not too much, not too little. Use the Reese equation and you'll never go wrong. Any questions? All right, that concludes the lab portion of the RF seminar series talk number 10 on noise diode calibration. Thanks very much for coming.